Hi students, today we are going to discuss about magnetic properties, which is our next chapter in third unit. Okay, what is that? Magnetic properties. Let us see what are the magnetic materials. So magnetism arises from the magnetic moment or magnetic dipole moment of the magnetic materials. Any material that can be magnetized by the application of magnetic field is called a magnetic material. That means now let us take a material. By applying the magnetic field, we will encourage, we will raising the magnetic properties of the particular material. Then it is said to be, whenever the material is reacted for the magnetic field, then it is said to be a magnetic material. So the concept magnetism arises from the magnetic moment or magnetic dipole moment of the magnetic material. We know whenever we play with the magnets, right? So in that magnet we are having two poles, north and south poles. Those are the dipoles. Okay. So when magnetism of materials is mainly due to the interactions of the uncompensated magnetic moments of the atoms or molecules. Means that is due to the interactions of the magnetic moments, magnetic dipole moments or magnetic moments of atoms or molecules. They have permanent or induced magnetic field. Okay, it may be the permanent or some induced magnetic dipole moments. Okay, now induced dipole moments in the presence of magnetic field. Okay, and next, magnetism. Let us see what is magnetism. The attracting property exhibited by the magnet is known as magnetism. And what is magnetic dipole? What causes the magnetism in a material? That is only the magnetic dipole. Magnetic consists of north and south poles. Any two opposite poles are separated by a finite distance constitutes a magnetic dipole. Okay, this is the magnetic dipole here. Okay, that means we are having two poles. This is a north and south pole. Okay, how the field will be? See here. And next, magnetic moment or magnetic dipole moment. Let us see the magnetic moment of permanent magnet. What is the magnetic moment? What is a permanent magnet? Let us see. Magnetic moment is, it is a product of pole strength and distance between two poles. We are saying, suppose let it be a north and south pole and separated by a distance. So it is a product of pole strength and distance between two poles. If M is the magnetic pole strength and L is the length of the magnet, L is the length of the magnet, then it is magnetic dipole or magnetic moment is given by mu M equals to 2 Lm ampere meter square. That is a permanent or magnetic moment of a magnet. So now magnetic moment of a current loop. It is a product of current passing through the conductor and cross-sectional area of the conductor. Let it be consider a current loop. And what is the magnetic moment in the current loop is the product of current passing through such loop. Then it may be a conductor and cross-sectional area of the conductor, whatever material, whatever the loop we are taking. Okay, so when an electric current of amperes I, that is a measure, flows through a circular wire of one turn having an area of cross section A, that is said to have magnetic moment of mu M. That's a micrometers. That means magnetic moment is indicating as mu M. Okay, that is I into A. Okay, current passing through the loop and area of cross section of the loop. Okay, it is a vector quantity pointing from south to north pole. So it is a pointer from which denoting it is from south to north. And next, magnetic moment of an atom. It is the sum of orbital magnetic moment of electron, orbital magnetic moment of electron, spin magnetic moment of electron, and spin magnetic moment of nucleus. So these are the magnetic moment of an atom. What is means all the sum of these. Okay. Next, magnetic field. The space surrounding the magnet to which its attracting influence is itself, it felt, is known as magnetic field. So the space surrounding the magnet up to which its attracting influence is felt, that is a magnetic field, we know in general. From where to where the field is acts, the how the magnet will attracts the things. Okay. And magnetic lines of force. The magnetic field is characterized by magnetic lines of force, that is the lines indicating the field. And magnetic field strength. So magnetic field strength H is the force experienced by a unit north pole placed at a point in a magnetic field. This is a magnetic field strength. That means unit north pole placed at a given point in a magnetic field. Whenever it forces, it experiences some force. That is H equals to F by mu m. Mu m is the magnetic moment. Okay. And next, magnetic induction or magnetic flux density B. The magnetic flux density B is defined as the number of magnetic lines. The number of magnetic lines of force passing through unit area of cross section of magnetic material. If I is the number of magnetic lines of force, that means see here, what is the flux density or magnetic induction? It is defined as the number of magnetic lines of force passing through unit area of cross section. So here we are considering a unit area of cross section A, and see how many lines are passing through that magnetic material. So now if pi is the number of magnetic lines of force that passing through our required area A of cross section of material, then the flux density V equals to phi by A. Now it is expressed in Weber per meter or Tesla. Okay. And next, magnetic induction or magnetic flux density. It is nothing but a same. Okay. So the magnetic flux density. In other words, okay, the magnetic flux density V is defined as the number of magnetic lines of force passing through unit area of section of a magnetic material. Let it be pi. Okay, same as it is, no change in this. Okay, and next, magnetization. The magnetization M is defined as the magnetic moment per unit volume. Okay, magnetic moment per unit volume is known as a magnetization. And magnetic permeability. The magnetic permeability of, it is a measure of the amount of magnetic lines of force penetrating through a material, that is a permittivity of a magnet. Okay, now it is defined as the ratio of magnetic flux density or magnetic induction or field strength B in the material to the applied magnetic field intensity H. That is, it is a ratio. Flux density is a ratio. It's a material. What is that? There is a B. There is a magnetic induction field strength B in a material to the applied magnetic field intensity H. Okay. Now mu equals to B by H. Now P equals to mu H. Okay. Henry per meter is a unit. Next, magnetic permeability of free space. We already discussed in the permittivity, permeability. Okay. In previous chapters also there is a permittivity, here is a permeability, relative permeability or permeability of free space. Okay, permittivity, relative permittivity, like that. So both in dielectric materials and magnetic materials, these definitions are most important for the entire chapter. The magnetic permeability of free space is a measure of the amount of magnetic lines of force passing through the air medium. So the name in the definition only, magnetic permeability of free space, then the amount of lines passing through the unit air volume, that's a through the air medium. Now it is a mu naught equals to B naught by H, where free space permeability, the value of permeability of free space is mu naught equals to 4 pi into 10 power minus 7 Henry per meter. Okay, and next, relative permeability mu or. What is relative permeability? It is defined as the ratio of permeability of a material to the permeability of a free space. So relative permeability means is a ratio. There is also in the dielectrics also we have the relative permittivity. That is also the ratio between the permittivity of a particular medium to the permittivity of free space. Then it is said to be relative permeability. Relative permittivity, like this only. Relative permeability also, it is defined as the ratio of permeability of a material to the permittivity of a free space. Don't get confused between permittivity and permeability. Permittivity comes in a dielectric materials, permeability comes in a magnetic materials. Okay, now mu r equals to mu by mu naught. Whenever we need the mu value, let it be written as mu equals to mu naught into mu r. Okay, and next, magnetic susceptibility. We know the term susceptibility very well from our intermediate. Now the ratio of the magnetization produced in a sample to the magnetic field strength, right, that equals to m by h. Okay, m by h. There is a magnetization, the ratio of magnetization m produced in a sample to the magnetic field strength h. The units gets cancelled because those two are in a ratio. Okay, and next, the relation between B, H and M. Okay, what, let us see. We know that B equals to mu H. B equals to, in place of mu we can write it as mu naught mu r, that into H. Now it will be mu naught mu r H plus mu naught H minus mu naught H. So we are both adding and subtracting those two terms. Now we know that M equals to H into mu r minus 1. Now B equals to mu naught H plus mu naught M. So from where these terms are getting? B equals to mu naught into H plus M. We are getting common. You have to, once you have to go through your textbooks, you may find a number of derivations like this. Okay. Now the relation between xi and mu1. Let us see. B equals to mu naught into H plus M. We know the value of mu naught, that equals to B by H plus M from this equation only. Now mu r we know that. By substituting this value here, now mu r equals to mu B by H and mu naught B by H plus M. Okay, now mu r equals to H plus M by H. Mu r equals to 1 plus M by H. Now mu r equals to 1 plus M by H represents the magnetic susceptibility. So xi equals to mu r minus 1. So we obtain a relation between xi, susceptibility, to the relative permeability. Okay, so simply this is the basic definitions we have to learn. Must and should for this chapter is all those.